Hello students, I am Dr. Tanmoy Biswas. I welcome you all in my channel Chemistry, the Mystery of Molecules. Today's topic of discussion is one MCQ is in front of you. I request you student, please pause the video, try by yourself, and whatever answer you get, please write in the comment box with a brief explanation. Don't hesitate whether your answer will be right or wrong, because self-evaluation is essential for improvement. And don't worry, after some time you will get the answer with proper explanation. Now let's start. If you look at this problem is a multiple step reaction, and that's why it is very important to understand the reactivity of the reactant as well as the reagent. First LDA, then TMSCl or trimethylsilyl chloride, and third is zinc bromide benzyl chloride. What is the product? Let's learn it mechanistically. Now question is, you can see this is an LDA molecule. This LDA is selective proton abstraction reagent because of the presence of these two big isopropyl groups. That's why it can't act as a nucleophile and it can attack here. It can only abstract protons. Okay, so it is actually a selective base. Now from where this base proton will be abstracted? From more acidic site, and more specifically if I say two types of proton abstraction possible, so option HA or HB. This HB is relatively less acidic, although it is vinylogous proton, but it is less acidic because this is far apart from this carbonyl group. So only the minus R effect of carbonyl group will operate because of the principle of vinylology, or it's a vinylogous system. Okay, whereas if you compare this option, this HA, here both minus R as well as minus I will operate. So means this is more acidic, so it will be abstracted and produces this carbanion species, and this carbanion is resonance stabilized. How? This will give and it will open up, so it will produce, this is the CH2 double bond, this is the O minus, this is, and this is the. Now in the next step, this is a silicon substitution or silicon ether formation. How? These will act as a nucleophile, this O minus, and attack this silicon center Cl leave, and this is first addition of nucleophiles, then departure of nucleofuge or Cl minus. Now in this case, generally the chemistry of enolate or nucleophilic attack by enolate happens from this carbon site. In this case, why this happened from this oxygen side? Because of the stable oxygen silicon bond formation. Why? Because oxygen has lone pair of electron in p orbital, and that can overlap with the vacant d orbital of silicon efficiently. So in this way, although the silicon oxygen bond is a single bond, but it is some more stable compared to single bond. You may consider it's a partial double bond character, and because of this electron delocalization, this bond gets stabilized. That's why here the attack happens from oxygen side, and this is one of the exceptions, student. Generally the nucleophilic attack of enolate happens from this carbon side. So in this way, these silyl enol ethers are produced, because this is silyl, this is enol, and this is an ether. Okay, so these silyl ether are nucleophilic in nature. Why? Because of this canonical form, means here you can see the lone pair of electron donated and it comes here. So in this way it produces the negative charge here. This is the double bond, this is the Si-Me3, this. So because of this it produces, because of this, these carbon act as a nucleophile. And by the way, question, is it a very strong nucleophile? Answer is no. Why? Because nucleophilic property is coming through charge separation, this form negative and positive, and we know in resonance, if any canonical form is associated with charge separation, the stabilization of that canonical form is less, or contribution of that canonical form into the overall electronic distribution is less. So its percentage less and contribution less, and you may consider this is less reactive. So in principle it should act as a nucleophile, but because of this it is less reactive, and for that purpose, in order to make the reaction happen, what is done? Reactive substance needed which can produce carbocation type derivative. So you can see this is a benzylic chloride. we know that benzylic system can produce carbocation efficiently, and this is like a, means you may consider like a substitution reaction can happen efficiently. But why the chlorine will leave? This chlorine will leave efficiently by the coordination with this zinc 2 ion, because we know these zinc 2 centers are Lewis acidic, so it will coordinate to this chlorine and help it will leave. There is no guarantee that free carbocation will be produced, but after this coordination, these benzylic center will be more reactive for chlorine leave. So consequently, if the nucleophile is less reactive, then also the reaction will happen, and ultimately it will produce this benzylic substituted carbonyl derivative, or more specifically alpha beta unsaturated carbonyl derivative. So this is the answer. Now in this case, what are the key steps and name reaction associated with this process? First step is the proton abstraction by bulky base like LDA, or selective proton abstraction. Second is enolate formation, and means enolate stabilization, means this oxygen anion production, and that oxygen anion reacts, means the nucleophilic substitution on the silicon center happens. And third step is enolate formation and carbon-carbon bond formation via nucleophilic substitution in presence of zinc bromide as Lewis acid. So Lewis acid mediated CC bond formation. So in today's discussion, what is the answer? Answer is option C. Now question, why not the other options? If you look at little closely, that this center can never produce carbon ion, so option A is gone. Option D, if you look at, I have given electrophilic benzylic system, this it is not nucleophilic, and zinc 2 center, not metallic zinc, so nucleophilic attack on the carbonyl by benzylic system not possible, so this is gone. Now competition between C and B and C. Okay, so if you look at for B, the carbonyl need to produce from here, which is less acidic, so not possible, gone. Option C is the answer. Now if this question is given to you in your exam, how can you solve this less than 30 seconds? First of all, you need to understand from where the LDA will abstract the proton, and LDA is actually a selective proton abstracting reagent, or it's a bulky base, not nucleophile, and it will abstract proton from less bulky as well as more acidic side, and that is here. Second, trimethyl silyl chloride is actually a enolether formation or enol protecting reagent, gone. Third is zinc bromide plus benzylic chloride. It is a very reactive substrate for both SN1 and SN2. So in short, in nucleophilic substitution reaction. So here carbonyl will be generated, and that will ultimately means after this enol formation, it will react with benzyl chloride and nucleophilic substitution will happen. What option closely matches? Option C. Okay, and this option A and D not possible. Competition is B versus C, but because of more acidity, carbonyl will be generated here, reaction will happen. So less than 30 seconds you can do, and for that purpose, more practice, more knowledge, and such kind of MCQ practice is essential, and try to keep your mind cool in the exam hall. That will give the best result. So in conclusion, what you have learned today, LD is a bulky and strong base, it abstracts protons selectively. Methyl group closer to carbonyl is relatively more acidic because of vinylogous methyl group, because in case of vinylogous methyl group only -R works, whereas closer to the carbonyl -I and -R both works. And enolate could be protected by silyl ether formation. And finally, zinc 2 plus is Lewis acidic, and it helps to generate the benzylic carbocation by chloride removal through Lewis acid base interaction. And finally, the carbocation can react with silyl enol ether and forms carbon-carbon bond. This is a very good strategy to prepare CC bond. So this is the end of the discussion. I believe this video may be useful for you. If it is, please help this channel to grow. And if possible, please visit my another channel where I upload global warming and climate change related videos. So thanks for watching. Stay happy, stay blessed. See you in my next video. Bye bye.